Okay, the first section in chapter 4 is the production of the sound waves. First, we should understand how a sound starts. A sound wave begins with a vibrating object. So, the vibrating object sets the air molecules in motion, and this vibration travels throughout the gas or air. So, we hear this vibration as sound. And right here we should be careful about this source and wave. Because source produces the wave, frequency of the source only determines the frequency of the wave. And when a wave is produced, its frequency is the same as the source. You can change a wave frequency only if you change the frequency of the source. So nothing else can change the frequency of a wave. The simplest sound wave is the sound of a tuning fork. A tuning fork is this, so it's a metal object at the length L, which has two prongs. One of them is this, second one is that. As the prong of the tuning fork swings to right, so it swings back and right continuously, right and left. As it swings to right, so as you see here, the air molecules are forced close together. Yani this tuning fork, when it moves to right, it forces the air molecules to compress and produce a region which is at high density and high pressure. Such a region of high molecular density or high air pressure is called compression. But later this tuning fork is first going to right, then coming to left. So when it moves to left, this time it do reverse. So it produces a region which is at low air pressure or low density. Such a region is called the rarefaction. So then, as the tuning fork vibrates right and left, back and forth, so it produces a region of high pressure, a region of low air pressure, high pressure, low pressure, and then so continuously it vibrates and it produces in the air regions of high, low, high, low, high, low, high, low air pressures or high, low densities. So because the vibration is moving in horizontal, as you see, it's vibrating horizontal. So wave is also moving horizontally and in the same direction of vibration. So we say the sound waves are longitudinal. And in sound waves, the vibration of air molecules are parallel to the direction of the wave motion. So sound waves are longitudinal waves. So we can also represent the sound wave by using a sine curve. How? Remember, we said that some regions are at higher pressure. This region is at a high pressure, low pressure, high pressure, low pressure, high pressure, low pressure, high pressure, and so on. So the region which is at high pressure corresponds to a crest. So high pressure is high, but at the rarefaction pressure is low. High pressure, again low pressure, and high pressure. So as you see, this is a sine graph. What does this graph represent? This graph represents how pressure is changing along a sound or longitudinal wave. So high air pressure, low air pressure, but this is the atmospheric pressure. Continuously pressure is changing as the sound is traveling through the air. When the tuning fork vibrates with simple harmonic motion, so the air molecules also vibrate back and forth with simple harmonic motion. So then remember, we said that the frequency of the wave is just the same as the frequency of the source, or behavior of the wave is the same as the behavior of the source. And source produces the wave. For that reason, if source is vibrating with simple harmonic motion, wave is also vibrating with simple harmonic motion. Now, so can you hear all types of vibrations? No, we can only hear a vibration as a sound, a kind of vibration as a sound, if its frequency is between 20 Hz and 20,000 Hz. So we say these waves as audible sound waves. But we cannot hear the frequency smaller than 20 Hz or greater than 20,000 Hz, but some animals can hear. Sound waves with frequencies less than 20 Hz are called infrasonic waves. Elephants can hear that sound. They use the infrasonic sound waves to communicate, even separated by many kilometers, because these waves are very long longer wavelength waves, so they can travel very long distance. Their large ears enable to detect these low frequency sound waves. But some other animals, such as the dogs, can hear a wave which is greater than 20,000 hertz, which are called ultrasonic waves. Not only dogs, but also bats or dolphins, even they can hear the ultrasonic waves. Maybe that's why the dog is giving a quick response to whistle, because whistle is a high frequency wave. For that reason, or high frequency sound, for that reason the dogs give a quick response to a whistle. Now, frequency determines the pitch. So what is pitch? Now, in fact, they are directly related to each other, pitch and frequency. Frequency is the number of vibrations of a sound in 1 second. So it's, in fact, number of the vibration of the source. However, pitch is a subjective quantity. What you perceived or what you heard, what you hear is called pitch. Yani source produces a sound with a frequency, and we hear, or human ear hear a sound with a pitch. So for that reason, we say that frequency of a wave is a objective quantity. Yani you can measure it, but pitch depends on the observer. So I can hear a sound at a greater pitch, or a smaller or lower pitch. So in the Doppler effect, we are going to explain this in details. So pitch is simply how high or low we perceive the sound is to be known as pitch. But this how high or low does not refer to volume. It refers thin or thick sound. Yani high frequency sound or low frequency sound. As the frequency of a sound wave increases, the pitch rises. So we say the pitch rises, we don't say the pitch increases. Okay, next one is the speed of a wave. So speed of a wave depends on the medium. So only thing which determines the speed of a wave is the medium. For example, look at here. Sound wave in gases, in air, which is 25 degrees Celsius, is 346 meters per second. But in water at 25 degrees Celsius, it is 1,490. In iron, 5,130. As you see, the same sound can travel in gases slowest, in liquid faster, but in solids fastest. Why is it like this? The speed of the wave depends on how quickly one particle can transfer its motion, or in fact, to say vibration better, to another particles. So solid particles are so close to each other, for that reason they can easily transfer the vibration from particle to particle. Liquid are also close, but gas particles or molecules are very far from each other. For that reason, they cannot transfer the vibration very fast. That's why the wave or sound travels in gases slowest, in liquid faster, but in solid fastest. As you see, maybe you have seen before the cowboy listening to rails. Why is it doing that like that? Because he wants to hear the sound of a train, but air, in the air, sound travels very slower. So how many times slower? Nearly 5 times slower than the solid. So that's why sound is coming very fast in the rail. That's why he can hear the sound of a wave, sound of a train, even if this train is so far from that region. So we said that the speed of the sound is determined by the medium. So as the type of the medium changes, speed of the sound in that medium changes. Second thing which changes the speed of a wave or sound is the temperature. So look at here. There are some temperatures given. Air at 0 degrees Celsius, at 25 degrees Celsius, at air at 100 degrees Celsius. As you see, as temperature increases, speed of the sound also increases. Why? Because as temperature rises, the particles of the gas molecules collide more frequently. So initially they are vibrating with a smaller amplitude. When the temperature of the gas molecules increases, they start to vibrate in a longer amplitude. That's why the average separation between the particles or the molecules are decreasing. That's why they quickly transfer the vibration from particle to particle. However, in liquid and solids, the particles are close enough together that that difference due to the temperature does not make so much difference. Yeah, it makes a difference in the gases, but in solid and liquids, increasing temperature does not make a noticeable change in the speed of the wave. Sound waves propagate in two dimensions. How can we understand this? Because when I was talking, or you are talking to somebody, everybody behind, up, down, left, right can hear you. This proves that sound is traveling in all directions. When a sound is produced in a room, it can be heard throughout the room because the sound is spread in all directions. So, if the sound wave is spreading in all directions, so we can say that sound waves are approximately spherical. So, yani, if your mouth is the center of the sound, so when you talk, the sound waves are expanding on an area of sphere. And this can be represented with series of circles surrounding the source. Why series of circles? You cannot draw the sphere on a paper. That's why you are going to draw it as a circles. So each circle here represents, in fact, a sphere, which is a compression. So this model, these lines represents a compressed region. This is another compressed region. This is another compressed region. So these compressed regions or compressions are called a new name, which is wavefront. Wavefront, wavefront, wavefront. So each wavefront corresponds to a crest of the sine wave. Remember, high pressure of crest, high pressure, crest. So between two compressions, of course, there is rarefaction. It's not drawn in this model, but we know that between two compressions, there is rarefaction. Rarefaction corresponds to a trough. The distance between adjacent wavefronts is one wavelength. We know that distance between two compressions is one wavelength. So distance between two wavefronts is again one wavelength. The radial lines perpendicular to wavefront are called rays. So these lines are called rays. What do they show? They show the direction of the expansion, in which direction the wave is expanding. These radial rays, radial means on the radius, shows the direction of the wave motion. So wavefront of a small portion of the spherical wave that is many wavelengths away from the source are nearly parallel planes, and the rays are nearly parallel lines. What does it mean? If you take this small portion of this wave, it's a little, as you see, spherical. But if you take the same length of portion of a longer wavefront and larger wavefront, so it becomes a little straight. When you take another one, so as the wavefront is moving away from the source, a small portion of that wavefront becomes nearly straight, plane. That's why when the wavefront is very far from the source, these very small portion of these wavefronts are almost parallel to each other. Such waves are called plane waves. Next title is the breaking the sound barrier. Now, what is this about, breaking the sound barrier? In fact, it's not, you are not breaking something. In this breaking sound barrier, it's about the source moving at higher speed. Now we are going to see in this picture 1, 2, 3, 4 airplanes. The first airplane's engine is working, but the airplane is not in motion. So it is at rest. As you see, wavefronts are expanding in all directions with the same wavelength. So between two wavefronts, the distance is the same, wavelength is the same. But if the airplane starts to fly, the wave fronts in front of the airplane comes closer. So wavelength in front of the airplane becomes shorter, but behind the wavelength becomes longer because of the motion of the wave. If the wave flies with speed of sound, what happens? In this case, the wave sound released from the airplane and the airplane itself starting to move together. For that, as in front of the airplane right here, the sound accumulates. What does this mean? So sound is a wave. When one wave and two waves accumulate, what happens to its energy? Its energy increases. If you continuously add So another wavefront to the resultant wave. So the amplitude of the resultant wave increases, and amplitude of the wave determines its energy. Remember, square of the amplitude. Then you are going to hear here, you are going to get here a very big power of wave. So for a short time, you are going to hear this big power of energy of the wave as a shock wave. It's a sonic boom, a sudden sound you are going to hear. But if the airplane exceeds the speed of the sound, in this case, it is called to breaking the sound barrier. Yani if an airplane is flying at a speed which is greater than speed of the sound, you are going to say that this is known as breaking the sound barrier. So at that speed, which speed of the airplane is equal to speed of the sound, you are going to hear a sonic boom, which is called the shock wave. Just once you are going to hear a big boom, because the air sound accumulates at what region. When it exceeds, the waves are making this proposition on the edge of the airplane. So at that region, they make this proposition. They are proposed. For that reason, when the airplane exceeds the speed of the sound, you are going to observe, if you watch the movie, on the edge of this airplane, there are some clouds. Appears to be some clouds. These clouds, in fact, are because of the high pressure, most probably it's the vapor in the air becomes water in the air becomes vaporized and gives a light, a color of the light, it's very white, like a cloud. So when the speed of the airplane exceeds the speed of the sound, the shock wave will be at the edge of the plane and purpose to give a huge explosion. So this is called breaking this sound barrier. Now let's answer the two conceptual challenge questions. One of them is at page 102. It says, suppose you hear a singer in a radio cassette across the room, so it can be a singer in the room too. Comprehensions and rarefactions from the sound waves reach your ear, and you interpret these vibrations as sound. Yeah, we only hear the vibrations as sound because our ears are created in such a capacity. Were the air particles that are vibrating near your ear carried across the room by the sound wave? How do you explain this? In fact, remember, wave particles are not carried. They are just vibrating and transferring the energy from particle to particle. So vibration is moving. We said that, remember, in wave motion, disturbance is moving, but the particles are only vibrating. One particle transfers its vibration to another one transfers to another. However, they stay their own places. They are not moving across the medium. Question number 2 says that light waves travel nearly 1 million times faster than sound waves in air. With this in mind, explain how the distance to a lightning bolt can be determined by counting the seconds between the flash and the sound of the thunder. So when you see the flash, because speed of the wave is light is very fast, as soon as you see the flash, in fact, the light, you see the source. You see the at that moment, nearly almost at that moment, the thunder occurs. However, you are going to hear its sound sometime later. Why? Because speed of the sound is smaller in air, so it takes time to travel from the center of the ball to you. So you are going to count the time. Remember, distance is equal to speed multiplied by time. We know that what speed of the sound is. It is 340 in air, almost average. Multiplied by, you are going to count the time. How long does it take for the thunder to reach your ear from until the flash? Say that it's 6 seconds. Later you heard the thunder. So when you multiply this two, you are going to get the distance between you and the center of the thunder. So the Doppler effect, in fact, is a very good opportunity to understand the difference between the pitch and the frequency. Okay, in this example, in fact, we know that if you increase the frequency of a source, you are going to hear a high-pitched sound. But this is not the only case. Assume that here is a car moving on the road, which is horning continuously. Here is an observer at point A, another observer at point B. As the car is moving towards the left, the wave fronts between in front of the car, so the wavelength becomes shorter. So wave fronts approaches each other. However, behind the car, because it's moving to left, the wavelength right there becomes longer. However, for these two observers, because the sound is traveling in air, so speed of the sound in air is constant for these two observers. The one which hears the sound with a shorter wavelength will hear a higher pitch because the speed of the sound is constant. The one which observes the longer wavelength will hear a low pitch right here. So for that reason, the observer in front of the car and the behind car will hear a different pitches even if the source frequency is the same. So this is a very good example about the difference between the pitch and the frequency. So frequency of the car is the same, but because of the relative motion, because the car is approaching to the observer at point A, observer at the point A hears a higher pitch, but the observer behind the car, because the car is moving away from this observer will hear a lower pitch. It's going to perceive a low frequency. This observer will perceive a high frequency, which is called perceived frequency as pitch. What is the causal Doppler effect? So relative motion between the source and observer creates the change in the frequency or in the pitch. So now assume that an observer is standing on a street and the driver hears the same pitch as the horn of the car park. Now assume that there's a parked car not moving, so somebody continuously horning. Driver is at rest according to this park. The observer in the standing observer also at rest according to this car. For that reason, both hears the same pitch. However, when the car and observer relatively approaches each other, as you see right here, this relative motion affects the wavefronts of the sound waves, and the wavefronts reach the observer more often. As you see, these wavefronts are approaching the observer wave more frequently. Does this observer perceives a greater frequency, which is we said higher pitch. When the car and the observer relatively move away from each other, now these cases, the wavefront reach the observer less often. As you see, distance between two wavefronts is long. This observer will hear the wavefront less often. So this observer perceives a smaller frequency or lower pitch. Then maybe you can make a generalization. If the observer and the source approaches to each other, so observer will hear a high pitch. If source is moving away from the observer, or they move from each other away from each other, so the observer will hear a low pitch. So now we are going to study these cases one by one. If the sound source approaches the observer, so observer is at rest. So what's going to happen? Because they are approaching to each other, so going to hear a higher pitch than f. To make f prime greater than f, you should subtract v source from v. So to make the denominator smaller denominator means a greater number of the division. So this is the equation for if the source approaches to the observer, which is at rest. If the sound source moves away from the observer, this time, because it's moving away in this case, so the observer will hear a lower pitch. To make this smaller, you should add vs with v. So you are going to make this denominator greater. Greater denominator means smaller f, the pitch. If the observer approaches the source, you are going to write the observer speed to the numerator, not denominator, because source will be written to the denominator, observer will be written in numerator. This v, both are the speed of the sound in air. So this is random for it doesn't change. If observer approaches the source, sound source, so that in this case source is equal at rest. So because relatively they are moving each other, getting closer to each other, so what's going to happen? We'll have high pitch. To make this higher, greater than f, you should add v plus vo. But if the observer moves away from the sound source is at rest, assume that the car is at rest, but you are running towards the car, pitch will drop. To make this smaller, of course, you should subtract vo from v and make numerator smaller, so this will give a smaller pitch. If both sound source and observer approaches each other, so you are going to combine these two cases. Because observers approaching, so you are going to make it positive. If the source is approaching, you are going to make this negative sign. You are going to get a very, very high pitch sound. If both sound source and observer moves away from each other, in this case, you are going to hear a very low pitch sound because they are moving very away from each other. Source and the observer is moving from each other. So to make this very low, you should subtract VO from V and you should add VS to V, and you should get a very low number for F prime. So this frequency shift is known as the Doppler effect. So Doppler effect occurs whenever there is a relative motion. This is the key word between the source of the waves and the observer. Yani observer and source must approach each other or move away from each other. If relatively they approach to each other, so observer will hear a high pitch. If relatively they move away from each other, the observer will hear a low pitch sound. Now right here, maybe general cases for all cases. This is your general equation. F prime, which is the pitch, frequency of the pitch, is equal to frequency of sound. V plus minus V observer, V plus minus V source. If source moves away from the observer, you are going to say that you are going to put here positive. You are going to make it positive. So you are going to drop the pitch. If the source approaches the observer, so observer will high pitch. To make it higher, you should put it a negative sign. So that in general, you can say that if source approaches to the observer, you are going to put the negative sign for each of them. But if source moves away, which is the car is the source, which makes the sound. If source moves away from the observer, you are going to put positives for the source. However, if observer approaches the sound source, in this case, observer will hear a higher pitch. In this case, you are going to put the positive for observer approaching. As you see, observer is also approaching, try to approach, so put positive sign. But if observer moves away from the car, in this case, you are going to put negative sign for observer. So this is the general case for the Doppler effect. So let's solve an example. Page 121, review and assess question number 13. It says that a police car moves at a speed of 90 km per hour and emits a siren of frequency 1000 Hz. So this is the speed of the source, because police car emits a siren. So it's the speed of the source, 90 km per hour. And siren has a frequency which is objective quantity F, 1000 Hz. What is the frequency of the sound detected? When it says detected, it refers to pitch. Yani F prime is asked by a standing observer. So standing means observer is at rest. For that reason, you are going to write for observer at 0. As the police car approaches. So if approaches, pitch rises. Speed of sound is 340 meters per second. First, we should convert kilometer per hour to meter per second. So every kilometer is 1000 meters. Every hour is 3600 seconds. So when you do this calculation, result 25 meters per second. Now, remember your equation as F prime is equal to F V plus minus V observer divided by V plus minus V source. Because the observer is at rest, so it is 0. So you are just going to write here V. The police car approaches to the standing observer. Observer will hear a higher pitch. To make it greater, you should put here a negative sign. So then, in this case, write the number. F is 1000. Speed of the sound made is 340. The question is given 340 minus 25. So answer becomes 1080. So question number 13, review and assess question, page 121. A parked ambulance emits a sound of frequency. So parked ambulance, it is the source. Source is at rest this time. Sound of frequency, this is the objective quantity, 1200 Hertz. It is the frequency F of the source. What frequency is detected? When it says detected, we are going to understand F prime is asked. We will find the pitch by an observer moving with a velocity of 20 meters per second. So this is the observer, VO, is moving with 20 meters per second. In first case, towards the ambulance, yani approaches to each other. Of course, f prime will be greater than f. We can understand this because high approaching towards each other. Away from the ambulance, in this case, f prime will be smaller than f. We can simply understand this. If observer approaches the parked ambulance, so pitch will rise. Approaches keyword. To make it greater, you should write here positive. You should make the numerator positive, make greater number. So 1200 is f. Speed of the sound v. Speed of the source, this is the observer, is 20. Speed of the source is 0 because it's at rest. The ambulance is at rest. Divided by, again, speed of the sound. It hears 1270. As you see, f prime is 1270 is greater than 1200. So f prime is greater than f. So as we expected. And if the observer moves away from the park, so this positive sign will be negative sign in this case because pitch drops. So then 1200, 340 minus 20 divided by 340. So answer becomes 1129. As you see, 1129 is smaller than 1200. So f prime is smaller than f, as we expected again. Now let's answer the section rule questions. What is the relationship between frequency and pitch? Yes, when the frequency of the source increases, pitch rises. If frequency of the source decreases, pitch drops. But this is not only cause which changes the pitch. And remember, in Doppler effect, relative motion between the source and observer also determines the pitch. Sound pulses emitted by a dolphin travel through 20 degrees ocean water at a rate of 1,450 meters per second. So this is the speed of the sound in ocean wave. In 20 degrees Celsius air, these pulses travel with 342.9 meters per second. How can you account for this difference in speed? Remember, in water, molecules are very close. In air, molecules are very far from each other. So vibrations quickly transferred from molecule to molecule in water, but very slowly transferred from molecule to molecule in air. For that reason, speed in air is smaller than speed in water. Next one, could a portion of the innermost wave front shown in figure be approximated by a plane wave? Why or why not? Remember, if it is closer to the source, a very small portion cannot be approximated as a plane wave because it's spherical. However, if the wavefront is far from the source, in this case, this wave can be approximated as a plane wave. And the condition is what? The wavefront must be far from the source relative to the wavelength. Yani 1 wavelength, 2 wavelength, 3, 4, 5, 6 wavelength away. It must be away from the source. In this case, we can treat as spherical wave as a plane wave. Figure 4.8 is a diagram of Doppler effect in ripple tank. Ripple tank means it's the tank in which the water experiments are done. In which direction is the source of the ripple waves moving? Remember, Doppler effect is available not only for sound, in water, in light. So Doppler effect can be observed for all kinds of the waves. So remember, right here in front of the in the direction of the motion of the source, the wavelength will be shorter. So right here the wavelength is shorter. For that reason, we can understand this source is moving to left.